guys, welcome to another lesson. Hope everyone is okay. All right, so we're just going to start from where we left off last class, which is on moles. All right, so we looked at the some equations and also did some calculations regarding mole. So we're just going to actually continue from there. All right, so on last class we looked at just different compounds singularly, right, and finding the mole or the mass. Now we're going to look at chemical reactions or equations and do calculations regards to mole. Right, so if we look at this equation, it says that 2 Mg plus O2 gives us 2 MgO. Right, so in regards to mole, what this is saying is that we have 2 moles of magnesium that's reacting with 1 mole of oxygen gas to give us 2 moles of magnesium oxide. Right, so in terms of mass, we know that magnesium mass is 24, but we have 2 moles of it. So the total mass of magnesium in this reaction will be 24 times 2, which is 48 grams. Right, and oxygen O2, O is 16, so it's 2 of 16, which is 32 grams of oxygen, and it would produce Mg is 24, oxygen is 16, 24 and 16 is 40, but it's 2 moles of magnesium oxide, so it's 40 times 2 to give us 8 grams of magnesium oxide. All right, so if we notice now that the total mass of your reactant, which is 32 and 48, right, when you add that, you get 80 grams, which is equal to the total mass of your product that is formed. All right, so in this case, this is known as your conservation of mass in chemistry. Right, so mass or matter is conserved throughout. So so it's never created nor destroyed. So it's the same that was there before would be the same that is there after the products are formed. All right, so let's look at another one which includes gases. So in this case, we have 3H2 gas plus N2 gas gives us 2 NH3 gas. All right, so in this case, we have 3 moles of hydrogen gas reacting with 1 mole of nitrogen gas to give us 2 moles of ammonia gas. All right, in terms of particles, all right, so remember from last class, we noted that mole is equal to number of particles over Avogadro's number. So since we have the moles, we can multiply it by Avogadro's number to give us the amount of particles here. So for hydrogen, we multiply by 3 because it's 3 moles. Nitrogen, we multiply by 1, and ammonia, we multiply by 2. All right, in terms of volume, we have the mole, and remember, mole is equal to the volume of the gas over RTP or STP. So this case is STP, so the volume would be mole times STP value, which is 22.4 dm cubed. So hydrogen would be 3 times 22.4, nitrogen would be 1 times 22.4, and ammonia will be 2 times 22.4, and at RTP, we just changed 22.4 to 24 dm cubed. And in terms of mass, we know that hydrogen gas molar mass would be 2 times 1, which is 2, so multiply mole by 2 to give us the total mass. Nitrogen is 14, but it's N2, so it's 14 times 2 to give us 28, and it's 1 mole, so 28 times 1. And ammonia is 17, so we have 14 for N and 3 times 1 for hydrogen, give us 17, and multiply by 2 since it's 2 moles. All right, so let's look at when we're performing calculations with equations, right? So the first thing you do is to write a balanced chemical equation for the specific reaction, right? So you decide which reactant or product the question is concerned with. And then you determine the simplest mole ratio between these from the balance equation, write a standard statement connecting the two substances, and use a simple proportion to perform the calculation. All right, so let's look at some examples. So in this case, we have 0.05 mole of copper 2 carbonate. When heated, were heated, sorry, calculate the mass of copper 2 oxide formed and also the volume of carbon dioxide produced at STP. Right? So remember, the first step is to write a balanced chemical reaction. So we have copper 2 carbonate being heated, so that's copper 2 carbonate as the only reactant, and then when it decomposes, it gives us copper oxide and carbon dioxide gas, right? So we ensure that the equation is balanced, which it is, right? Then we move to the next step, which is identifying what we got. So in this case, we got the mole of copper 2 carbonate. So it's 0.05 mole of copper 2 carbonate that was used, right? But we know from the equation that it's a 1-to-1 ratio for all the compounds present, right? So it's 1 copper carbonate, 1 copper oxide, and 1 carbon dioxide. So we make the link between what we are given to what we want to find. So the link will be between copper carbonate and also copper oxide, right? So we have 0.05 mole of copper carbonate from our question. So that means it will be the same mole that will be for copper oxide because it's a 1-to-1 ratio, right? Now, it asks us to find the mass, right? So first we would have to find the molar mass of copper oxide, right? Because the only equation that we have for mass with mole would be mole is equal to mass over molar mass. So therefore, we need to find the molar mass of copper oxide, which is copper is 64, oxygen is 16. We add both and we get 80 gram per mole, right? So therefore, we know that 1 mole of copper carbonate is equal to, gives us 80 grams of copper oxide. So in that case, 0.05 mole of copper carbonate would give us X grams of copper oxide. We cross multiply, that gives us 80 times 0.05, and we get 4 grams of copper oxide that will be produced. All right, so that's clear for everyone?
Yeah.
All right, great. All right, so the second part of the question was to find the volume of carbon dioxide produced. All right, so again, it's the same process. We make the link from what we have to what we need to find. So it's a 1-to-1 ratio right throughout. So it's the same mole of carbon dioxide that is produced, 0.05 mole, right? And it says we need it at STP, and we know at STP it's 22.4 dm³ that it occupies. So therefore, the volume would be our mole times our STP value, and we get 1.12 dm³ of carbon dioxide that will be produced. All right, so that was one question. Let's look at another one. All right, so the mass of sodium hydroxide must be added. What mass of sodium hydroxide must be added to sulfuric acid to produce 7.1 gram of salt? All right, so and again, the first thing we do is to write or balance chemical equation. So we have 2NaOH plus sulfuric acid H2SO4 to give us Na2SO4 and 2 water H2O, right? So again, now we made the link for what we have to what we need to find. So we have the mass of the gas of the salt, sorry, right? And we need to know the mass of sodium hydroxide from our reactant, right? And also we make the link between the moles, right? So we know we have 2 moles of sodium hydroxide to give us 1 mole of Na2SO4, right? So in that case, we can find the mole of the salt being produced since we have the mass, right? So we need to find the molar mass of sodium sulfate, right? So the molar mass of sodium sulfate is 142 grams, right? And we know the molar mass of NaOH is 80 grams, right? So we have both molar masses. We have the mass of Na2SO4. We don't have the mass of NaOH. And in that case, we can cross multiply. So we get 7.1 times 80 and divide by 142, and it gives us the mass of NaOH to be 4 grams of NaOH must be added. Right? So if that is not clear, there is another way in using the equations to make it look clearer. All right, so we know that the mole is equal to your mass over your molar mass, right? And we're finding it for the Na2SO4 because we have the mass, which is 7.1, and it's being divided by your molar mass, which is 142. All right, so when we calculate that, it gives us a mole of 0.05, right? So our mole is 0.05 mole of Na2SO4, and since between this and this, it's a 2-to-1 ratio, so that means the mole of the NaOH would be 0.05 multiplied by 2, right? And this gives us 0.10 mole. All right, so now we have the mole, we can find the mass of the NaOH, which is your mole 0.10 multiplied by your molar mass, which is 80. Oh, sorry. The answer here is 8, sorry. So this answer, when you calculate this, you get 8. And also this would be 8 grams. Right? So you can do it this way in terms of making the link, or you can use it by using your equations from last week to actually calculate the value of your unknown. All right, so that's clear. All right, so let's move along. All right, so these are some additional questions that we can look at. All right, so let's try. All right, so I'm going to give you a chance to try the first 2 questions and see what your answers are. All right, so giving you about 5 minutes or to 10 to do the first 2 questions, and let's see what the answers given will be. All right, any answers for question 1 as yet?
Sir, what's the mass of aluminum?
Could you read that?
What is the mass of aluminum?
The mass of aluminum, 27. All right, so let me give you the masses in the table in your chat. So aluminum is 27, Cl 35.5. All right, so we have one person, 213.6 grams. All right, let us work that one together and see. All right, so it says 1 mass of aluminum chloride can be obtained from 48 grams of aluminum is completely reacted with dilute hydrochloric acid. So that means we have Al plus HCl to give us AlCl3 plus H2 gas. All right, and in order to balance this, it's and the 3 there. All right, so that's our balance equation. So we're given the mass of aluminum, which is 48 grams, right? And we need to know what mass of aluminum chloride. So we notice that the mole ratio is a 2-to-2 mole ratio, right? A 2-to-2 mole ratio. So whatever the mole of aluminum is the same mole of aluminum chloride that was produced. So we can find the mole of aluminum, which is the mass 48 divided by the mass of aluminum, which is 27, right? And that gives us 1.777, so that's 1.78 mole, right? So that's the same amount of mole for aluminum chloride. So therefore, we can find the mass of aluminum chloride since it's the mole, which is 1.78, multiplied by the molar mass, which will be 35.5 times 3 plus aluminum, which is 27, which is 133.5, and we get 237.63 grams. All right, so I think someone got it. Yes, that is correct. All right, so I hope that's what most persons got. All right, so you can move on now to question 2. Well, not really that hard. It's just practice. All right, so once you practice enough using the equations, then it becomes a little bit easier.
Sir, can you go over the answer for number 1 again, please?
Could you read that?
Can you go over the answer for number 1 again, please?
Sure. All right, so remember the first thing is to write your chemical equation, right? So we have aluminum reacting with hydrochloric acid to give us aluminum chloride and hydrogen gas. So we balance it by putting a 2 here and a 2 here to balance the Al. Cl3, which is 6Cl here, so we put 6 here to balance the Cls. And we have 6H here, so we put 3 here to balance over the H's, right? So we were given the mass of aluminum, which is 48 grams, right? So we're making the link between aluminum and the unknown, which is aluminum chloride. So we know this is a 2-to-2 ratio, which is basically whatever the mole of aluminum is the same mole of aluminum chloride. So to find the mole of aluminum using its mass, from last week we know that mole is equal to mass over molar mass, right? So the mass is 48 and our molar mass of aluminum is 27, right? So 48 over 27, we get 1.78 mole. So 1.78 mole of aluminum produces 1.78 mole of aluminum chloride. So we have the mole of aluminum chloride, we need to find the mass. So it's the mole times the molar mass of aluminum chloride, which the molar mass is 133.5. So it's 1.78 times 133.5, which is equal to 237.63 grams.
Okay, sir.
Sure. All right, so good question. So question is, why didn't we times the aluminum mass by 2 since we had 2 of them? All right, so remember the definition of molar mass. The definition states it's the amount of mass in a compound or atom of 1 mole of the substance, right? So and students normally make that mistake. Whatever number is before these compounds, we never use it when we're calculating the molar mass. The molar mass is just 1 mole of the compound. So if it's the molar mass of aluminum here, it's just the Al there. If it's the molar mass of the 6HCl, it's just the HCl. Right? So we never use a number in front of the compound to give us the molar mass, because the molar mass is only concentrated with 1 mole of the substance. All right, so that's answered the question. All right, so I think now you can, all right, let me, 133. All right, so the 133.5 is the molar mass of aluminum chloride, which would be 3Cl, which is 35.5 times 3, which is 106.5, plus it has 1 Al, and Al is 27. So we get 133.5 to be the molar mass of aluminum chloride. All right, so question 2 should be a little bit easier. It gave you the equation. All right, so go ahead and find the volume of hydrogen at RTP. All right, so someone. All right, the question though is the volume. So question two, we're finding the volume of hydrogen gas. And I'm seeing persons giving me the mass, which I think you're referring to question three. All right, so one person got 105.6 cm cube. All right, so let's see what the answer is before this time runs out. All right, so since it already gave the equation that gives us one part of our work is finished, right? So it gives us the mass of aluminum, right? And we want to know it for hydrogen gas. So that means we make the link between aluminum and hydrogen gas. And we notice it is a 2 to 3 ratio, all right? And we have aluminum, we have the mass of aluminum to be 60 grams. So that means we can find a mole of aluminum, which is the mass, so 60 grams over the molar mass, which is 27, and we get 2.22 mole, right? So that's the mole of aluminum. Because it's a 2 to 3 ratio, then the mole of hydrogen gas will be, all right, let's work it out so you can see. So it takes 2 moles of aluminum to produce 3 moles of hydrogen gas, but we have 2.2 moles of this, which is equal to x. So therefore x, so it will be 2 times x equals 3.3 times 2.2, all right, and divide by 2. All right, so therefore it's 3 times 2.22 over 2, and that gives us 3.33 moles. So that's the mole of hydrogen that is produced. And finally, we can find the volume, which is equal to your mole, 3.333, times the value at RTP, which is 24 dm3, and that gives us 79.92 dm3. Great. So that will be the answer of your volume. All right, since some persons are doing question 3, when we resume, we'll look at question 3 as well. All right, so I'm going to restart now. All right, so just to confirm, everyone got this explanation for question 2? All right, no. All right, I'll go over again. All right, so we have the equation right there in the question, right? So that's one step that is already done for us. So the question gives us aluminum, right? So it gives us the mass of aluminum, and where we want to know how much volume of hydrogen gas is produced. So that's all the part of the equation that we're going to use, right? So that means we take out the aluminum and the hydrogen. So we notice that it's 2 moles of aluminum gives us 3 moles of hydrogen gas. So that's a 2 to 3 ratio in regards to aluminum to hydrogen, right? So the question also says that we use 60 grams of aluminum, right? So in 60 grams of aluminum, we can find the mole of aluminum that was actually used in this reaction, because we know that mole is equal to mass over molar mass. So the mass is the mass given in the question divided by the molar mass of aluminum, which is just 27. So it's 60 times 27 to give us 2.22 moles of aluminum, right? So that's the amount of aluminum that was used. So we need to know what's the mole of hydrogen now, right? So because it's a 2 to 3 ratio, right? Then that means it's a 2 to 3 ratio. But in this case, instead of us having 2 moles of aluminum, we actually had 2.22 moles. So it's 2.22 moles to give us X moles of hydrogen, right? So we want to know what mole it is, so we cross multiply. So it's 2 times x to give us 2x, and 3 times 2.2, 2. Right? So we divide by 2. So the hydrogen mole will be 3 times 2.22 divided by 2 to give us the mole to be 3.33 moles of hydrogen. Right? But we don't want the mole of hydrogen, we want the volume. So another equation from last week would be that the mole is equal to volume over, and it said RTP at RTP, right? So therefore, the volume will be mole times RTP value. So the mole is 3.33 and RTP is 24. So we multiply those two to get our answer. All right, any of that's any clear? All right, great. All right, so let's focus on one last one, which is question 3, since some persons were doing question 3. All right, so giving you 5 minutes to try question 3, and then we can move on further into moles. All right, so someone got 2.38 grams for both. All right, so let's wait on one more answer, and then we confirm that answer.
Don't come here, she already do it. Give her a chance to clean up the room.
It says 6 feet.
Sorry, man.
Just the 4 6 4 4.
Huh?
Yeah, like the one. This is 1.
I don't think you know what 6.
All right, so let's go. Not seeing any more answers being provided. All right, so question 3 says 2.38 grams of black copper 2 oxide is completely reduced by hydrogen to give copper and water. What are the masses of copper and water formed? All right, so the first thing is to write our chemical equation. So it is copper 2 oxide, which is CuO, sorry, and it's being reacted with hydrogen gas. Right, and that gives us copper and water. Right, so that's our chemical reaction for this question. Right, you notice that it's also balanced as well, so we have a 1-to-1 ratio. And the question gives us the mass of copper oxide, which is 2.38 grams. Right? And we need to know what's the mass of these two products formed. So let's go with copper oxide to copper first. All right, so the first thing is to find our mole. All right, since we're given the mass, which is 2.38 divided by the molar mass of copper oxide. Copper is 64, oxygen is 16, so that is 80. All right, so we have 2.38 divided by 80, and we get 0.03 moles. Right, so because it's a 1-to-1 ratio, then 0.03 moles of copper oxide gives us 0.03 moles of copper. So therefore, mass of copper will be your mole multiplied by the molar mass of copper, which is 64, and that gives us 1.92 grams. All right, so question, where is this 80 come from? So the 80 there is your molar mass of copper oxide, which is copper is 64 and oxygen is 16. 64 and 16 gives us 80. All right, so we have the mass of copper, which is 1.92 grams. Right, and then the next part is the mass of water, sorry, which is the same 1-to-1 ratio because everything here is 1. So that means the mole of water is also 0.03 mole. Right? So therefore the mass of water will be the mole times the molar mass of water, which is 16 plus 2, 18, and we get the mass of water to be 0.54 grams. All right, so no, the masses ratio does not work the same as the mole ratio. So the only thing here works with the ratio would be your mole, right? So if it asks you to find the mass, you'd have to work it out instead of using the ratios, right? All right, any question before we move on from these areas? All right, so is it, all right, great. All right, so everyone, is it all clear for moles, but this part of moles, because we're not finished as yet? All right, so let's move on now to another topic regarding moles. All right, so this part of moles now has to do with concentration of solutions. All right, so we're going to look at solute solvent, which we know by now what are solutes and what are solvents, right? So in order to get a solution, both two aspects are needed to create a solution. So the solute is a substance that is dissolved. The solvent is what is doing the dissolving. All right, so when we talk about concentration or concentrated solution or a dilute solution, right? So instead of using the word strong and weak to describe coffee, we can use the terms concentrated as well as dilute. Right? So when it says that a coffee is sweet, is strong, that means it is concentrated with a lot of coffee in comparison to the amount of water that is being used. Right? So a concentrated solution will contain more solutes dissolved in a certain volume of solution, while the dilute would be less solutes dissolved in the same volume of that solution. Right? So in order to standardize the volume of solutions, we use 1 dm cube, which is 1,000 centimeters cube, in our calculations of concentration. So concentration of a solution is the mass of solutes dissolved in 1 dm cube of a solution. All right, so in creating our solution or concentrations of different solutions, we actually use our mass in comparison to the amount of solution that will be produced. So concentration is normally highlighted in two units, which are gram per dm cube or moles per dm cube. Right, and based on those two units, we can actually figure out what we're going to use for our equations. Right, so let's look at using 1 dm cube of a solution, and we add 58.5 grams of sodium chloride, right? So in this case, we have a concentration of sodium chloride at 58.5 grams per dm cube, right? So the concentration of the solution is also equal to 1 mole per dm cube, since 58.5 grams of NaCl gives us 1 mole of the salt, right? So the number of moles per dm cube of a solution is also known by the term of molarity. So once it's the mole per dm cube concentration, we can replace concentration there with molarity. So therefore, our equations now will be the concentration. If we're given the mass of the solute, it is the mass of the solute divided by the volume of your solution. Right? If we're given the mole of your solute, then it is the mole of solute divided by the volume of the solution. And finally, our molar concentration, if it asks to calculate molar concentration, is your mass concentration divided by your molar mass of the solution or the compound. All right, so let's look at it. All right, so we say a solution of sodium chloride is made by dissolving 11.7 grams of sodium chloride in 500 cm cube of a solution. Find the concentration of the solution in gram per dm cube and also in mole per dm cube. All right, so let's go to the gram per dm cube first. So the first thing is to ensure that our volume is in dm cube. All right, so we have 500 centimeter cube, so we divide it by 1,000 to get 0.5 dm cube. Right, so that's our volume of the solution. So the first part is concentration for the mass. So it's the mass divided by the volume. Right, so we're given the mass 11.7 grams and we divide it by the volume and we get 23.4 gram per dm cube. Part B now asks us in mole per dm cube. So that means we have to use the mass given, which is 11.7, to find the mole. And we know that mole is equal to mass over molar mass. And the molar mass of sodium chloride is 58.5. So it's 11.7 divided by 58.5, we get 0.2 moles. Right, so now that we have the mole, we can divide it by the given volume of the solution, which is 0.5 dm cube, and we get 0.4 mole per dm cube. All right, so is that clear on those two calculations? All right, so let's look at another example. So in this case, a solution of magnesium chloride has a concentration of 23.75 gram per dm cube. What is the concentration of solution in mole per dm cube? And if 200 cm cube of the solution is evaporated to dryness, what mass of salt can be obtained? All right, so the first part is to find the concentration in mole per dm cube, and we're given the concentration in gram per dm cube. So we can find number of moles in magnesium chloride in 1 dm cube, right? So the number of moles in 1 dm cube would be the 0.25 moles,
Wow.
right? Which is their mass over your molar mass. So 0.2375, which is given in the question, divided by the molar mass, which is 95 for magnesium chloride, and we get 0.25 mole. Right? So since we have the mole now, we actually can, that's our answer in dm cube because we're dividing it by 1 dm cube, since it's 1 dm cube of the solution that we found the mole for. Right? So we get 0.25 mole per dm cube. So that's part A. Part B now asks us how much of the salt will be obtained. So we have mass of solute is equal to mass concentration times the volume of solution. So the mass concentration is the one in gram per dm cube, which is a 23.75, multiplied by the volume of your solute, which is, it's given there 200 cm cube, and we change it to dm cube, so we divide by 1,000, so we get 4.75 grams. All right, so a similar one here, but in this case we're given mole per dm cube, and we need to find the gram per dm cube. All right, so in this case we have to find the gram in 1 dm cube. So the mass of the acid in 1 dm cube will be your mole times your molar mass. So your mole is a 0.25 times the molar mass of sulfuric acid, which is 98, and we get 24.5 grams. So therefore, in gram per dm cube, it will be 24.5 divided by 1, since it's 1 dm cube of the mole that we found, which is 24.5 gram per dm cube. And then for part B, what mass of the acid will be obtained in 25 cm cube of the solution. So we know that the acid is equal to mass concentration times the volume of the solution. So it's the 24.5 times 250 cm cube, so we divide it by 1,000 to get it in dm cube, and we get 6.125 grams. All right, so I'm let's all right, so I'm giving you this one to try. So it's 25 cm cube of a solution of sulfuric acid of concentration 0.400 mole per dm cube is neutralized with a solution of sodium hydroxide of concentration 0.625 mole per dm cube. What is the volume of sodium hydroxide solution required? All right, so there's a note there that mole is equal to molar concentration times volume, and we're asked to find the volume there. All right, so giving you 5 minutes to attempt, and let's see what answers we get. All right, any answers? All right, so one person has, how do you find the molar mass? Molar mass is the sum of individual atoms in the compound. So if you need to find molar mass of sodium chloride, it's sodium, which is 23, plus chlorine, which is 35.5. It's one of each, so you add both and you get the molar mass there. All right, so one person has 0.4 dm cube. All right, so let's check if that is correct. All right, so remember the first thing would be to have our equation, right? And our equation would be sulfuric acid give, so it's H2SO4 plus 2 NaOH to give us Na2SO4 plus 2 H2O, right? So we have our equation there, and we're given both concentration of sulfuric acid as well as concentration of NaOH. So number of moles of sulfuric acid to NaOH is a 1:2 ratio, right? So we have volume of H2SO4 times concentration over the volume of NaOH times concentration based on their ratio of their moles, right? So remember, mole is equal to concentration times volume, and that's what's there. So for H2SO4, its concentration was 0.025 dm cube. So the volume, sorry, was 25 cm cube, so we divide by 1,000, so we get 0.025 dm cube times its concentration, which is 0.400, right, over the volume of NaOH, which is what we want to find, times its concentration, which is 0.2625, right? And in that case, we get 32 cm cube. All right, so that might seem a little bit confusing, so let's break it up so you can see it better. All right, so we know that it's a 1:2 ratio, right, between the acid and the NaOH that we need to find, right? Now we know this formula here, that mole is equal to molar mass times volume, right? Well, we're only given the volume of the gas, of the acid, sorry. So we can find the mole of the acid, which is mole is equal to the concentration, which is 0.4, multiplied by the volume, right? But our volume needs to be in dm cube since our concentration is dm cube. So 25 divided by 1,000, which is 0.025. Right? And that gives us the mole of the acid, which will be 0.01. Right? So this is the mole of the acid that is used, and because it's a 1:2 ratio, then that means the mole of NaOH would be 2 times, right? So it's 0.01 multiplied by 2. So we get the mole of NaOH to be 0.02. Alright, so now we have the mole of NaOH and we need to find the volume. So from the same equation again up here, then the volume is equal to your mole divided by your concentration, right? So your mole here is 0.02 divided by your concentration, which is 0.625. And let me just confirm that it's the same answer, right? And you will get 0.032. But remember, this is in dm cube. So if you need to change it to cm cube, we multiply by 1,000 and you get 32. All right, so that's clear for everyone. All right, great. Anyone else has any problem before we move on? All right, so I'll take that everyone is good, so we can move on from this. All right, so that's it, what we're going to look for in terms of our concentration using mole. All right, so let's move now to volumetric analysis. So we're going to look at a little bit about titration. All right, so let's move to titration. All right, so we know that titration is a very unique, very unique topic or very unique process that's used in chemistry. So volumetric analysis is a method of finding out the quantity of a substance present in a solid or a solution. Usually involves titrating a known solution, known as a standard solution, with an unknown solution. All right, so for one, we have to know something, the concentration of one, and the other one is unknown. Based on the equation of reaction, calculations are then made to find out the concentration of the unknown solution, just like the calculations that we have done before. So a standard solution of titrant is the solution of known concentration, which is required to react quantitatively with another solution of unknown concentration. All right, so in doing titration, we notice that we use a pipette, right? So our pipette is, we normally have 25 cm cube volume of pipette. It's used to deliver volumes to our conical flask. So it gives us an exact 25 cm cube volume to our conical flask. The solution in the titrating flask is known as the titrate. Right, so before using the pipette, it should be washed with tap water, then rinse with distilled water, and finally with the liquid it is to be filled with. So that's very important. So each time you're doing titration, the pipette needs to be washed in tap water. Then you're going to actually rinse it with distilled water to ensure that you take away any impurities from it. Right, and then now before you add your titrate to it, you actually add some of the titrate to it to wash out any excess water that is remaining. Right. So for safety reasons, the pipette filler is used to suck up the solution. Right, so we use the filler in order to get the solution inside the pipette to the exact 25 cm cube mark. When the liquid rises to the level higher than the level, remove the tip of the pipette from the liquid and gently squeeze to release the excess liquid that is there. So read the meniscus So normally we ensure that it's above the mark, and then we release the excess to ensure that we get directly at the 25 cm³ mark. Right, so once you have the 25 cm³, then you actually release it into your flask. And now the burette. So the burette now is, so that's our burette on the right hand side. So let's look, how do we use the burette? So the burette is used to contain and measure the volume of the liquid called the titrant used in the titration. Before using the burette, it should be washed first with tap water, then rinsed with distilled water, and then finally with the liquid it is to be filled with. The liquid in the burette must be released slowly, a few drops at a time into the titration flask. Right, so the tap at the bottom of the burette should be turned slightly so we get drops of the liquid coming out. The readings must be taken accurate to 0.10 cm³. Example, we have 24.00 cm³ and not just 24 cm³. Make sure that the clip of the burette is tight and the liquid is not leaking. So each time you turn the tap to turn it off, there should be no liquid coming from your burette. Also make sure that the burette jet is filled with liquid. It must not contain any air bubbles. So when you're filling up the burette, no air bubbles should be present. Once there's an air bubble, you have to get rid of the air bubble, either by releasing the liquid to that air bubble until it disappears and then refilling it back up. Alright, so the burette should be clamped to the retort stand in a vertical position so the reading will be accurate. When reading the burette, the eye must be horizontal to the bottom of the meniscus. Right, so we all know how to read from measuring instruments. Alright, so when we do especially acid-base titration, which is the popular one, then we have to use an indicator in order for us to know when to stop the titration process. Right, so these are the different indicators that we use on a daily in the lab. So we have methyl orange, screen methyl orange, litmus, as well as phenolphthalein. So these are the colors when they are in specific type of solutions, right? So what we're looking at would be the endpoint colors. So depending on our indicator that we use, so let's say we use methyl orange, right? So we're dropping from our burette until we get that orange color. That orange color tells us that the reaction actually, that's our endpoint in our reaction. So we look for the orange color. If it's methyl orange, if it's green methyl orange, we look for the gray color. If it's litmus, we look for purple. And if it's phenolphthalein, we look for the pink color, right? So that's the reason why we have to drop by drop, right? And once we're doing it drop by drop, we normally stir the flask to ensure that we haven't reached the point as yet. All right, so in doing titration, we normally do one original reading, which is normally called the rough titration. All right, this is just to ensure that you're doing the steps right, right, and you're going to compare that value with your other ones. So we do the first one as a rough titration, just to ensure you're doing everything correct, and then you do other titrations and ensuring that you have at least two values that are very close or similar in reading, right? So we have the final burette reading and we have the initial burette reading. You notice that the initial burette reading does not necessarily have to be the same value. So you can actually fit it to the 0 point on your burette, or you can fit it to any point there, right? But the important part is if it's not at 0, or even if it's at 0, you have to make note of it, right? And then you make note of when after you make your drops, what's the final reading? So you minus both to give us our final reading for the liquid, right? So when we have a table like this, then the values that we're going to use will be the two values that are either similar or very close to each other. And in this case, it will be trial 2 and trial 4, because both times those volumes were the exact same volume. Right, so we use 24.80 centimeter cubed as the volume of the NaOH that is required. All right, suppose that in an experiment you are asked to find a concentration of solution of sulfuric acid by titrating 25 cm cube of the acid against a standard solution of sodium hydroxide of concentration 0.10 mole per dm cube, using phenolphthalein as the indicator. Right, so we first know how to set it up. Right, so in the burette we have the known, which is your NaOH, your sodium hydroxide, and then in your flask is your unknown sulfuric acid. Right, so now remember the table before, right? So we will drop the burette drops of NaOH in our flask of the acid, right? And because we're using phenolphthalein as our indicator, what color would be looking for to ensure that we reach the end point? So let's go back to the table so you guys can see. So what color will we look for? And it's, yes, so pink. Right, so we'll be looking for a pink color each time we drop our NaOH. Right, and let's say we got this as our reading. So again, we use the ones that are similar, which is trial 2 and trial 4. So the volume would be 24.80 centimeter cube. Right, so again, we'll start off with your equation, ensure that it's balanced, and then you do your calculations just like what we did before. Right, so we have the relationship between the acid and the base, which is a 1:2 ratio. So your mole of your base, because we have the concentration and we have the volume, right? So we multiply both, gives us your mole, and so it's a 1:2 ratio. So therefore, we find half of the mole of NaOH to be the mole of your acid, because it's a 1:2 ratio. So divide by 2. And now because you have the mole of the acid, you can divide it by your volume that of your acid that was used, and you get your concentration of the acid. All right, so that's how you actually find the values there. All right, so let's try this one together. All right, so find the concentration of solution of sodium hydroxide in gram per dm cube in a titration method using 0.10 mole per dm cube hydrochloric acid. All right, so these are the readings. No, we generally don't use the rough titration value. All right, so it's the two other values from your rough titration. All right, so let's go. What would be our volumes for each titration trials here? So the rough titration, what volume would we complete the table with? So what volume would we write here? We have the initial and the final, so it's 22.20. All right, and then trial 2 would be 22.1. Yeah, so 22.10. And then trial 3 would be 22.10. Right, so we notice that our rough is 22.20, and the other two times we did it, we actually got the same value. So in that case, we don't have to do a trial 4 here, right? Because we now have two values that are similar. Right, so these values will tell us that this is the volume of the acid that is used. Right, so we have the volume of the acid now. So let's see how we use that to find the unknown. All right, so we have the volume of NaOH. All right, so write the chemical equation, ensure that it's balanced, right? And then we move towards finding the mole of your acid. Sorry, this NaOH at the top should be the HCl. So this right here is HCl, right? So we find the mole, which is your concentration times your volume, right? So concentration times volume gives us the mole. So that's the mole of the acid that is produced, right? And the relationship between, or the ratio between NaOH and HCl is a 1-to-1 ratio based on your equation. So that tells us that it's the same mole of NaOH that is present in this reaction. So now we can find the molar concentration of NaOH, which is your mole divided by the volume. And since it was in the pipette, it's always 25 centimeter cube. We divide it by 1,000 to get it in dm cube. So we get the molar concentration of NaOH to be 0.088 molarity. All right, but it asks for the mass concentration. So therefore, the mass concentration will be your molar concentration multiplied by your molar mass. So NaOH molar mass will be 40. So you multiply both and you get the 3.54 gram per dm cube. And that's, right? And that would be your answer. All right, so is there any questions regards to that? All right, so I'm going to give you this one to try now. All right, so you're going to complete the table and calculate the concentration of sodium hydroxide solution. All right, so let's check if that is our answer. All right, someone else got 0.2196. All right, so let's see. All right, so remember the first thing is, let's fill out the table first. All right, so we will have, for the first one is 24.40. Trial 2 would be 24.50. Right, this one would be 23.60. And the last trial would be 24.40. All right, so question. Which volume did you use the 0.40? Yep, so that's our volume that we'd use. All right, so let's go with our equation now. So the equation would be sodium hydroxide and hydrochloric acid. So it's NaOH plus HCl to give us NaCl and water. All right, so it's already balanced, so it's a 1-to-1 ratio throughout. All right, and we need to find the concentration of sodium hydroxide. All right, so we know the concentration of hydrochloric acid, which is 0.225 mole per dm cube. We know the volume of this, which is 25 cm cube. We also know the volume of the acid, which is 24.40 cm cube. Right, so first thing would be to find the mole. This is a 1-to-1 ratio. Then the mole of NaCl will be equal to the mole of NaOH. Right, so therefore the mole of HCl would be equal to the concentration multiplied by the volume, right? So the concentration is 0.225 times the volume. It's in centimeter cube, so we divide it by 1,000 to get it in dm cube, right? So that is 0.0244 multiplied by 0.225, and that's mole is 0.005 mole, right? So that's the mole of NaOH as well, right? Because it's a 1-to-1 ratio. So we have mole now, so we can find the concentration, which is equal to mole divided by its volume. So the mole is 0.005, and the volume is 25 centimeter cube, so we divide by 1,000 to get it in dm cube, which is 0.025, and we get 0.2 mole per dm cube. All right, and I think, all right, so the person that had the 0.2196, yes, you get that, because I think you use more than 0.005 as your mole, so that is correct. Great. All right, so is that clear for everyone now? All right, so for any calculation with acid-base titration is the same process that will be required, right? So there's nothing new in terms of moles that you need to do. The only thing is just to fill out the table if it's not being filled out. All right, so everything else is the same process as doing any other calculation regarding mole. Right, so for the last less than 10 minutes that we have, we're going to look at the last thing under mole, and then we're finished with this section of mole. All right, so it's not even a hard part, so I left the easiest part for last. So empirical formula and molecular formula, right? So the percentage of composition means the mass of each element in a compound divided by its molar mass times 100, since it's a percentage. So what this is telling us is how much percentage of a compound does each individual atom or element actually occupies, right? So that's what percentage composition tells us. A chemical formula shows the mole ratio of elements in a compound. There are two types of formulas, either the empirical formula, which shows the simplest mole ratio of elements present, or the molecular formula, which shows the actual number of moles of each element present. So the empirical formula is the reduction or the simplest ratio of each element present, right? While the molecular tells us how many or how much of each element was actually bonded together in order to create this compound. In most cases, or in some cases, the empirical formula is equal to your molecular formula because it cannot be reduced any further. All right, so let's look at some. So example, empirical formula of water is H2O. The molecular formula is H2O because we can't reduce H2O to any further. Because to reduce it, we have to divide by a common number that can go through both of those and leave no remainder, right? And then for CH2, empirical formula, molecular formula can be notice it's just being multiplied, so it can multiply these two by 2, so we get C2H4, can multiply by 3, sorry, we get C3H6, multiply by 4, C4H8. Right, so those are compounds that you will look further into. CH3, also it can be C2H6, right, because multiplying it by 2. So finding the molecular formula. Propene has an empirical formula of CH2. The relative molecular mass of propene is 42. Find the molecular formula of propene. right? So it gives us the simplest form of propene, which is not actually the formula of propene. We're given how much mass propene has, which is 42. So to find the formula, the molecular formula of propene is, we find, right? So in this case, we use the empirical formula, which is CH2, all right? And then bracket N there means what multiple of N will give us actually that mass. So N there represents the multiple that we can multiply the C and the H by, right? And the total of those masses will give us 42. So what we have is that C has a mass of 12, while H2 is 1 times 2, which is 2. So, and then that's multiplied by N to give us 42. So we have 14, N equal 42 divided by 14, so N there is 3. So the empirical formula will be multiplying CH2 by 3, so we get C3H6. So that would be the empirical formula of propene. All right, so let's look at another one. A compound on analysis was found to contain 85.7% carbon and 14.3% hydrogen. Determine the empirical formula of the compound. If the RMM of the compound is 42, determine its molecular formula. All right, so let's go. So the empirical formula, so we have the percentage of each element in the compound. So for carbon, its percentage is 85.7, hydrogen is 14.3. So we have the percentage, right? And we know percentage is out of 100, so that means the mass in 100 gram of the compound is basically 85.7 and 14.3, right? And then the RAM, which is your atomic mass for each, carbon is 12, hydrogen is 1. So we divide both by their atomic masses, right? So we get 7.14 and 14.3. And from here, we would divide by the lowest number, or the lower number in this case, which is 7.14 on both sides. All right, so we get a 1 to 2 ratio in regards to C and H. So therefore, the empirical formula would be C, 1C and 2H, so CH2, right? But now, since it gives us that the part B that says that the molecular mass is 42, then to find your molecular mass from your empirical mass is the same as before. So it's CH2N, right? So it's 42 divided by your 14, CH2 is 14, and we get 3. So it's C, so multiply the 3 by the CH2, and you get C3H6, right? All right, so now your time. So go ahead and try this one, and then we can finish for today. All right, so you have 2 minutes. Should not take more than that. All right, so before it ends, all right, so I'll see you guys next week. Well, next class, sorry. All right, and we'll take up from here. You'll give me your answers for what you got for this question. Then we can move on. All right, but we're finished with moles now. All right, so see you guys next